let's start with our warm-up question, which is related to what you guys did at the end of last week. So which of these skeletal structures are isomers of C5H12? Maya? Yes, that's correct. Oops. Let's do this. All right, so it's 1 and 2 only. We've got a 5-carbon alkane, and only 1 and 2 have 5 carbons. Remember, it's the bens and the ends. This one has 6. So that is not going to be an isomer. So this is a typical kind of, I've seen a number of questions about isomers in the question bank that are either using structures, skeletal structures, condensed structural formulas, things like that. I'll give you some more question bank practice as we get a little bit further into here. But that's a pretty typical question. All right, so I want to do a couple things today. I want to start out with this concept of homologous series. So if you'll turn to page 3 in your study guide. We've already pretty much done what's on page 2 in terms of the different types of structures. We've already talked about that with the other packet. So a homologous series is basically the same structure, the same molecule, but with additional carbons added on. So a longer carbon chain. So the simplest one is a series of alkanes. So we can have methane, ethane, propane, butane, pentane, etc. That is a homologous series where they tend to have very similar chemical properties because they have the same types of atoms. Whereas we might have a different family, which we'll talk about those different classes of compounds, the alcohols, where instead of a hydrogen, we've replaced one of the hydrogens with a hydroxyl group, which gives us an alcohol. So we have methanol, ethanol, propanol, butanol, et cetera. That's a homologous series of alcohols versus the homologous series of alkanes. Any of the functional groups in organic chemistry can be in a homologous series, can have a homologous series just with adding more carbons. And this is actually a pretty common database IA type topic. So how do different properties change as you go down a homologous series? I will show you guys a sample IA dealing with the alcohols. You usually want to go a little bit more in depth than just primary alcohols. We'll talk about secondary, tertiary, stuff like that a little bit later. But it's a very common thing to use because the homologous series, it makes for a nice independent variable of like how many carbons are in the chain and how does that affect your property of interest. So that's always a possibility if you are interested in doing a database IA. Because those they have similar chemical properties, but their physical properties tend to change as we go down the series. So, for example, in the homologous series of alkanes, this is going from methane down to octane, looking at boiling point in degrees Celsius. And you can see that methane's boiling point is at a negative 164. So it's pretty much a gas under almost all conditions. That's not super far from absolute zero. But that boiling point increases as we get longer and longer and longer. And we'll talk a little bit more about that later this week. But this becomes really important for things like refining crude oil. So this is a schematic of a fractionating column in an oil refinery where they pump in the crude oil and they heat it, and the lighter stuff becomes a gas sooner and pops off at the top of the fractionating column. And so you get your propane and other bottled gases at the top. And then as the melting or the boiling point changes, you end up with denser and denser substances that get used for different things. Right. So we'll come back to this question of boiling point a little bit later, but that's the basics of a homologous series. And doesn't work. Here we go. Okay, go ahead and skip to page 5. Again, page 4 we've mostly done with the skeletal structures, etc. So now we're going to start talking about these functional groups. What happens when you have something more than just carbon and hydrogen? And there's something other than just a branch of carbons. And there are a bunch of functional groups, and you have to know them. And right now, it's going to feel like a rote memorization task, and I strongly recommend flashcards, either online or physical ones. You'll find lots of stuff online for this because this aspect of organic chemistry is one of the things that gets tested on the MCAT. So there's a million, quizzes about functional groups in organic chemistry and things like that. So I'll find some links and post them, but I'm sure you'll be able to find way more than I can. So a functional group is basically a group of atoms within the molecule that are usually stuck together and that give the molecule a characteristic set of chemical properties, particular reactions that they undergo, particular physical properties as well, due to the presence of other electronegative elements like oxygen or nitrogen, and other changes in the structure. So you're not going to have to do too much with naming the functional groups the way that you did in the packet for the alkanes. We'll do a little bit with that, but so that you understand what's going on in the charts in your study guide. The way this is set up is, or the way the naming system is set up, we've already kind of dealt with prefix and stem, and a little bit with suffix. So the stem of the name of the compound is going to be the longest chain of carbons, the meth, eth, prop, but, etc. The prefix is going to talk about the substituents, which are the branches off of the main chain. What kind of branches do you have? Where are they located? And that's also going to apply to our halogens, which we've also covered already. The suffix is going to tell you the functional group. The only two suffixes we've used so far, suffixes? I don't know what the plural of suffix is, are ane and ene, right? So the ane tells you that it's an alkane, that there's only carbons and hydrogens, only single bonds between the carbons. The ene tells you that there's at least one double bond between the carbons. There's a whole bunch more for all of the different types of functional groups. Okay. So if you look at the table that starts on that page, you see the columns are the class, which is the type of molecule. We refer to the alkanes or the alkenes. The name of the functional group, which is it's going to give you the functional group here, which is also going to tell you, it also gets used in the naming scheme, but again, you're not going to have to use that very much. But this is where the YL here is where we get there's a methyl group coming off of this. So we had a branch with maybe 2, 3 dimethyl something. So the YL for the alkanes just means there's a group that consists of just an alkane, a chain of carbons coming off of our main carbon chain. And we already know that it's A and E for the suffix. The enes are alkynyl, not alkyl, and they end in ene. And we didn't really talk about triple bonds, but it just is a Y instead of an E, so alkynes instead of alkenes or alkanes. So these are just the basics with just carbons. They are still considered functional groups because you can have a branch coming off of a main chain that gives it a different structure. But then we start getting into adding oxygens, and things start getting fun. So the next two classes of molecules have the same functional group, which is the carbonyl group, which is just this C double bond to O. And the difference between them is that in the case of the aldehydes, let me back up. Let me back up and talk about the R. What is this R thing? So the R is just referring to some chain of carbons that this functional group is sitting on. So the R, imagine it's a carbon and then whatever else is attached to that carbon. Could be just a methyl group, could be a whole chain of 20 carbons with this at the end of it. And then you'll see sometimes, like on the ketones, R prime is just a different chain. So what they're showing in the third column is the functional group, the structure of the functional group, and its setting within the molecule. So aldehydes are always at the end because they're connected to whatever carbon chain you have here, and then the other bond to that carbon is a hydrogen, which ends the chain. It can't bond to anything else. Okay. And that it's written in our condensed structural formula as CHO. So if you see CHO in a condensed structural formula, that's an aldehyde. And it ends in al. You add the al at the end. So ethane becomes ethanal if it's 2 carbons. If you had 3 carbons, it would be propanal, etc. For a ketone, that carbon that has the double bonded oxygen, that carbonyl group, is in the middle of the chain. So it's got carbons on both sides. And at that point, we need to, most of the time, indicate where in the long chain that is. The example they give here is propanone. There's 3 carbons. We have just CO as our condensed structural formula. And this is a typo. There's an extra A in there. It's just propanone. So that second A should not be in there. So the one is the ketone, and the al is the aldehyde. Now, how do you keep track of which one has the hydrogen and which one has the carbons on both sides? Well, aldehyde has an H in it, so that's the one with the hydrogen. So now we're starting to get into things that are going to give our molecules a little bit of polarity, because that carbon-oxygen bond is going to be pretty polar. And so there's going to be some interesting possibilities going on there. Plus, those oxygens have 2 lone pairs, which are just, electrons looking for somebody to play with. So they can also get involved in some different reactions. And we'll see some of those typical reactions later in the unit. We've already talked about the alcohols. I kind of put it out of order so that you could see the aldehyde and the ketone together. The hydroxyl group is the OH group. So it's just going to sit on the end of whatever carbon you have, or just 1 carbon in the case of methanol. Now, the carboxylic acid is like a cross between an aldehyde and an alcohol. Okay, it's got the carbonyl group and it's got the hydroxyl group, and the whole thing together is called a carboxyl group. So this is carbonyl plus hydroxyl. Oh, I didn't talk about the ending here. The alcohols end in -al, just like the aldehydes end in -al. Alcohols end in -al. The carboxylic acid ends in an oic acid. This is methanoic acid. If we had another carbon there, instead of that hydrogen, it would be ethanoic acid, which is also known as acetic acid, which is also known as vinegar. It's an acid because there's this hydrogen really is only held on very loosely and can be lost very easily. We'll talk more about that when we get into acids and bases. But the presence of the hydroxyl group in conjunction with this oxygen drawing electrons away from this carbon really pulls electrons away from this hydrogen and makes it pretty easy to pop off. So these are our carboxylic acids. We'll be talking a lot about these. Organic acids tend to be weaker acids than things like hydrochloric acid, which is what we use a lot in the labs. You wouldn't want the same strength of hydrochloric acid on your salad as you put vinegar on your salad, or the same concentration. But they are, in fact, acids. All right, now we can also have oxygens that aren't just coming off of the side of the chain, but actually integral into the chain. And there's two ways we can do that. We can have an ester where we have a carbonyl group and an oxygen, and that second oxygen is connected directly to the rest of the chain. And this, we'll be talking about esters later. I'm possibly doing a lab related to esters. But they're named, their naming is a little bit funky. It's, this is methanoate, and there's a methyl group on it. So you talk about methyl methanoate. So it's a little bit complicated. I don't think they're going to make you, I haven't seen an example of them making you name an ester. They might give you the name of an ester, and you might have to recognize that it's an ester. Or they might give you both the name and the structure. But you do need to know what an ester group looks like. An ether group is without the carbonyl. It's just an oxygen in the middle of the chain. And how do you remember the difference between these two? The way I've heard is there's carbons on either side, or there's R's or carbon chains on either side of the oxygen, and so it's ether either. I don't know. I don't know if that's helpful or not, but I could actually change this to there's a chain on either side, as opposed to the ester that has the carbonyl next to on one side of the oxygen. So that's all our oxygen-containing functional groups. We also have some nitrogen-containing functional groups. Nitrile is just, the functional group is just a carbon triple bonded to a nitrogen. And this is also going to be at the end of a molecule, always, because this nitrogen is going to have a lone pair, and it's not really going to want to make another bond. Right, so if we think about, some folks were asking some questions in first period about how do you know who's going to make a bond, who has lone pairs, et cetera, without going through the whole Lewis structure process. Well, if you think about the Lewis diagram of the elements themselves, nitrogen has 5 valence electrons, so it kind of has 3 spots to fill. And it's going to make 3 bonds to fill those spots, and then it's going to have a lone pair. Right? Whereas oxygen, 2, 3, 4, 5, 6, only has really 2 spots to fill. And so it's going to make 2 bonds, which could be a double bond, and have 2 lone pairs. So that's, so there's like, a lot of these are currently drawn with invisible lone pairs on the oxygens and the nitrogens. So the other two outside of the nitrile are the amines and the amides. And this is kind of, the amide is kind of like an ester in that you have the carbonyl group plus an amine group, basically. So carbonyl plus amine makes something that is called a carboxamide functional group, which makes no sense to me because it doesn't have a hydroxyl group on it, but I didn't make this up. I didn't name these things. Whereas our amine is just coming straight off of the chain. The nitrogen is coming straight off of the main chain without an oxygen hanging out over here. So it's just the nitrogen with its 2 hydrogens and its lone pair. And so these are all going to be at the end of the molecule, like our aldehydes, like our, it's going to be at least at the end of the branch, but usually we have, if we have something like this, that gets included in the main chain. So these are going to be at the end. Those are our nitrogens. We've already talked about the halogenoalkanes, or sometimes people call them the haloalkanes. I don't know that it makes that much of a difference. This should be switched, as somebody pointed out in first period. But this is just one of the halogens sitting on the carbon. And this one, this goes into the prefix, not the suffix. So the halogens are the functional group that lives in the prefixes. All the rest have a suffix. Well, the phenyl groups also sometimes live in the prefixes. So phenyl groups are basically a benzene ring stuck onto something else. So we've talked before about how benzene has the alternating double bonds, which are aromatic. They have resonance, which means they can flip back and forth, but they don't really flip like pinball machines. They circulate around the ring, which is why it's often drawn like this with a circle in the center. So this and this mean exactly the same thing. Just another representation of those delocalized electrons. So if you see a ring like this, it's a phenyl group. Or you're not going to have any others that look like this. Okay. Questions? This is not an exhaustive list of organic functional groups, but these are the main ones that get used the most often. So that's why they're on your list. The next page, page 8, has a set of molecules, and it asks you to state the class and the functional group. So name it. Is it an alkane with an alkyl functional group? Is it an alcohol with a hydroxyl functional group, etc.? And then I'd also like you to circle the functional group on that sheet. Obviously, if it's an alkane, you don't have to circle anything because there's nothing to circle except the whole molecule. So go ahead and do that. And I will put a pause on this recording.